Today our topic is voltage divider bias. Okay, so voltage divider biasing method. So in previous class we talked about two different types of biasing method. One is fixed bias and other one is collector to base bias. What do you mean by fixed bias? In fixed bias, there is a less stability. Yes, in fixed bias, stability is very poor. Whereas in collector to base bias, stability is increases or compared to fixed bias. In collector to base bias, stability is better, we can say. Okay, other type of biasing method is voltage divider biasing method or potential divider biasing method. We will see today in detail about this method. So already we discussed fixed bias and a collector to base bias. Today we will see the voltage divider or potential divider or self bias method. Today we will see in detail about this one. Okay. So before going to that, you have to remember any circuit for analyzing in biasing, you have to remember these points. One is understanding the type of configuration and note down the input output, input current and output input current and input voltage, output current and output voltage, and find the coordinates of operating point. That means VCE comma IC. We have to find the VCE comma IC and apply the input side KVL to find out the input current. Similarly, apply the output side KVL to find out the output voltage. So here by applying the KVL, we will find the input current IB. Input current IB. Second step is use the input current and amplification factor to find out the current. To find out the output current. So output current in common emitter means IC. So IC is equal to beta IB we will get. And output KVL we find the output voltage. What do you mean by output voltage? This one is the output voltage VCE. So VCE we will find and also IC we will find. So this is the operating point VCE comma IC. This is called operating point. Okay, we will apply these steps for the following voltage divider circuit. So this is the voltage divider bias circuit. This is a transistor. So we have two resistance R1 and R2. So this is the voltage dividing node. So there is no base resistance. So collector resistance is there RC and emitter resistance is there RE. Okay. So here voltage is VE means emitter voltage here separate. But this base terminal and emitter terminal there is exist a voltage we call it as base emitter voltage. So output side there exists a voltage we call it as collector emitter voltage. So this is the collector terminal, this is the emitter terminal. So in between we call it as collector emitter terminal. So this same this one is the DC biasing. So battery voltage we are given for switching on to transistor. So the same circuit can be written in legibly. We will see here. So same circuit, one transistor. This terminal is emitter terminal. Okay. This terminal is emitter terminal, base terminal, and collector terminal. So here emitter resistance. This one is the collector resistance. So this is the R1, this is the R2. So what is the main difference between this circuit and this circuit is we are taken I1. Here also I1. In the previous we have taken I2, because if IB is very less, then we will same current, I1 current only flows. Consider IB is equal to very less. So IB is equal to very less means only one current. So I1 current will flow, R1 and R2. This is the base current. This is the collector current. This is the emitter current. So emitter current is nothing but base current plus collector current. So base current. So current is flowing from base to emitter here. So base current and also collector current. So IC is the collector current. Okay. So we will see one by one how to derive this equation. We will see circuit analysis. We can say that circuit analysis. Okay. So find the IC. What do you mean by IC? So IC is equal to, IC means what? Collector current. So collector current is equal to, how to find the collector current? Our basic formula is I is equal to V by R. So collector current, how to find the collector current here? So this is the collector current IC. How to find collector current? So VCC here, VCC by R1 plus R2. That is called, sorry, it is I1. So I1 is equal to VCC by this one, I1. So I1 is equal to VCC by R1 plus R2. Okay. What is the voltage across resistance R2? How to find resistance R2? I want to find the voltage here, this resistance. How to find? If we know this voltage, then only we will find. Okay. So we call it as V2. We call it as V2. So voltage across resistance R2. So what is the voltage in between means? So this we have to write this way. So V2 is equal to, general formula is V2 voltage is equal to current into resistance. So across R2 means, see across, I am asking across R2. So what is the resistance? Here means R2. So what is the current? What is the current? Current is equal to voltage VCC by resistance. Current is equal to voltage by resistance. VCC by, what is the resistance? Total resistance R1 plus R2 is the total resistance into this one is the R2. Okay, this is the voltage. Understood this one? It is the voltage dividing method. We are finding the voltage V2 here. Across R2 means, this is the formula. So first V2 is equal to basic formula, current into resistance. Across R2 means it is R2. What is the current? Current is equal to V by R. What is the V? DC voltage VCC by R means, what is our total resistance R1 and R2, and this resistance is as it is. Okay. This is V2. So applying the Kirchhoff law to the base circuit. So this is the base circuit. We have to write the Kirchhoff law. What do you mean by Kirchhoff law? Kirchhoff voltage law we have to write. So V2. So V2. So base circuit means this is the base circuit. V2, VBE and VE. Okay. So this point, some voltage is there. That voltage we call it as VE. That voltage we call it as VE. Okay, so concentrate. You can concentrate already. We crossed two biasing techniques. If you learn about two biasing, previous biasing circuit, it is very easy. Just voltage dividing method we are using. Just this extra terminals are R1 and R2. That's it. So here we are using V2 input bias circuit. Here base we are writing KVL, Kirchhoff voltage law, to this loop. So this node and VBE and VE. This node and VBE and VE. Okay. We have to write like that. What is, so V2 is equal to VBE plus VE. VBE plus VE we have to write. So what is the basic? So this is the KVL. We have to write the KVL from V2 to here. So first one is basic V2 minus other voltage VBE minus, and here voltage is VE. So from this equal to 0, from this we have to write V2 is equal to VBE plus VE. Okay, understood? I have to write here. So V2 is equal to VBE plus VE. So the VE means emitter voltage. From this equation, what I will write means V2 is equal to VBE plus, what is VE? VE means emitter voltage. So emitter voltage is nothing but, so it is the emitter voltage. Emitter voltage is nothing but emitter current into emitter resistance. So that means emitter current into emitter resistance. So VE means voltage. Voltage is equal to IR, I into R. So respective terminals are IE into RE. Understood? From this equation, what is IE? So IE is equal to V2 minus VBE divided by RE. Understood this equation? IE is equal to V2 minus VBE by RE. So from this equation, I can write it as IC. IC is equal to V2 minus VBE divided by RE. Because IC is equivalent to, since IC or IE is identically equivalent to IC. We know this is the basic formula. All emitted electrons are collected by the collector. Only few of the electrons are recombined with the base. That's why base current exists. So 95% of electrons are crossed the junction and collected by the collector. So that's why emitter current is equal to collector current. Emitter current is equal to collector current. Okay. So IC is equal to V2 minus VBE by RE. Okay. So collector current is equal to, this is the equation. So here you can observe in previous methods, so collector current depends on temperature. If temperature increases, VBE increases, then beta increases, then IC increases. So here not like this. If IC depends, from this equation we can conclude that IC depends on V2, VBE, RE. But V2 minus VB means, so this VB is negligible. So V2 is the maximum. Okay, that means V2 is very, very greater than VB. We are neglecting the VB also. So V2 is the maximum here. So because it is the resistor dividing voltage, V2 is the. Okay, so in practically VB is the independent, correct? So IC depends only V2. Okay, IC depends only V2. So this circuit almost independent of transistor parameter. So these are the transistor parameters. So VBE, RE, beta, beta, these are all transistor, IC naught, transistor parameter. But from this equation, I can say that this collector current is the independent of transistor parameters. Correct? Because V2 is the maximum, so IC is the dependent only on V2. Okay, that's why if temperature is increases also, nothing will happen. So we can maintain this stability. We can maintain the collector current at the output side. That is the meaning. Okay. Next, we will write the collector emitter voltage, KVL. We have to write the collector emitter voltage. Okay. So what is the collector emitter voltage? Collector emitter voltage, that means VCE. Applying the KVL to this one. So VCC minus ICRC minus VCE into IERE. So this is the output KVL. Okay, I wrote here to observe. First one is VCC is equal to ICRC. VCC is equal to ICRC plus VCE plus IERE. See how I write means from this. So VCC minus IC into RC, KVL output side. IC into RC minus VCE, some voltage is there in between, VCE voltage, minus IE into RE. Okay. So this is the output KVL. So from this equation, I will write VCC is equal to IC common, so RC plus RE. Actually here IC common, so RC is as it is. So from this we know that IE is identically equal to, so IE is identically equal to IC. Here IC means this is also IC, okay, replaced by IC. So IC common means RC and RE plus VCE. Okay. So therefore VCE is equal to, from this equation, VCC minus IC into RC plus RE. IC into RC plus RE. Okay. So what is the stabilization here? From the above, in previous equation, what is the previous equation? IC is equal to V2 minus VBE by RE. This is the previous, just now we seen. So collector current is independent of transistor parameters. Collector current is independent of transistor parameter from the above equation. So therefore V2 from this equation, so V2 is equal to VBE, from the above equation I am writing VBE plus IC RE. So you cross multiply IC RE is equal to V2 minus VBE. So V2 is equal to VBE plus IC RE. Okay. So here, so whenever you have one analogy here, whenever collector current is increases, whenever collector current is increases, I will show here. Whenever this collector current IC is increases, there is a voltage drop across emitter resistance is increases. If it is increases, base resistance is decreases. If base resistance is decreases, So IC value comes into original position or original value. Okay, that is the analogy here. So whenever current IC current is increases, voltage across emitter and voltage across emitter resistance is increases. This in turn IB is increases. If IB increases, this in turn reduced value of IC current to its original value. So that is the analogy. So here also it is independent of temperature. Okay, here also it is independent of temperature. So how to find the voltage divider method, I will explain in this slide. Voltage divider, nothing but, so this is the resistance, okay. So here one transistor just now is in our circuit. So this value we call it as V2. This one is R1. This one is R2. So this terminal is VCC. This one is ground. Okay. So this is the collector, emitter, and base. So from this, how to form the Thevenin or voltage dividing method, how to form, we will see. So how to find V2? So V2 is equal to V Thevenin voltage. V Thevenin voltage is equal to VCC into R2 by R1 plus R2. Already I told how to get this one. So V Thevenin is equal to IR. I will explain here. V Thevenin is equal to IR. Across R2 means this is R2. What is I? VCC by I is equal to current. Total resistance is equal to R1 plus R2 into this R2. So the same thing I wrote here. VCC R2 by R1 plus R2. So what is R Thevenin RTH is equal to two resistance R1 and R2 means R1 parallel R2. That means what is R1 parallel R2? So R1 R2 by R1 plus R2. This is the remainder. So the same circuit can be replaced. The same circuit can be replaced in this way. So this is the transistor. Okay, same circuit can be replaced. So this is the R Thevenin RTH. So this is the VTH. So V Thevenin voltage, and this one is the emitter resistance, and this one is the collector resistance and VCC. Same circuit will redrawn by using voltage divider method. Okay. So from by using this circuit, we can write the KVL. What is the KVL? So VTH I wrote here. So VTH input KVL is equal to IBRB plus VBE plus IB into IB plus IC into RE. IB plus IC into RE. Okay. See VTH input KVL. VTH is equal to, so IBRB. IBRB means this one. IBRB plus VBE plus IB plus IC into RE. Okay. So I will explain this. So VTH is equal to IBRB plus VBE plus IB plus IC into RE. Okay, so Thevenin voltage is equal to, what do you mean by Thevenin voltage? So this voltage is equal to IB RB. So that is base current and base resistance plus VBE plus this resistance IC, IB plus IC into RE. Understood? See, V Thevenin. This is the input KVL. I am writing this one. This is the path. So VTH minus IBRB minus. So R Thevenin is nothing but IB into RB, base resistance. This is base resistance now. R Thevenin is equal. This is the base resistance. So base resistance IBRB minus, what is the voltage here? VBE. And again, what is the current here? So IB plus IC. So base current plus collector current in this. Into what is the across resistance RE. Okay. So understood? So this is the final equation. So differentiating with respect to IC and considering the VBE to be independent of IC. So what is the differentiation? Dou IB by dou IC. With respect to IC means this term is 0. With respect to IC is equal to dou IB. So IB term is there means dou IB by dou IC into RB term, RB. Then 0. This is the VBE means constant, it is 0. Then plus, here IB term is there. Dou IB by dou IC into IB into RE. So here RE term is there. Okay. Plus here IC into RE. So we are differentiating with respect to IC means we will get RE term. Okay, we will get RE term. Understood this one? So I am differentiating with respect to IB, IC. So first term is 0, that is equal to, so dou IB by dou IC into RB plus this is the constant value means the differentiation is 0 plus, so IB into RE. So dou IB by with respect to IC means dou IC into RE plus, here only IC term is IC into RE means with respect to IC means we will get RE. Okay. So from this we will get dou IB by dou IC is common. What we get? RB plus RE, RB plus RE, correct, is equal to minus RE, because so is equal to means right hand side is this equation, we will divide into right and left. So finally, what is dou IB by dou IC? Dou IB by dou IC is equal to minus RE by RB plus RE, RB plus RE. So this is the final equation. Dou IB by dou IC is equal to minus RE by RB plus RE. Okay. So we have to substitute this equation into stability factor. What is the equation for stability factor? I wrote here, S is equal to 1 plus beta by 1 minus beta into dou IB by dou IC, dou IB by dou IC. So we know that dou IB by, so this is the dou IB by dou IC. So we have to substitute here dou IB by dou IC. So minus RE by RB plus R1. Yeah, already it is minus means we will get here plus term. So S is equal to 1 plus beta by 1 minus beta. Already minus is there, means it is plus beta into RE by RB plus RE. RB plus RE. Okay, understood this derivation? Okay. Now we will see so this is the in previous we will get we got this one. So S is equal to 1 plus beta by 1 plus beta into RE by RE plus RB. So we have to, from this we have to, S is equal to, we will write same thing, 1 plus beta. So we have to cross multiply. So 1 plus beta into RE by RB plus RE. So cross multiply means we will get RB plus RE plus beta RE divided by RB plus RE. So we will, this term is comes here, RB plus RE. Okay, so same thing. So this same equation I will show here. So up to now we got here. So stability factor S is equal to 1 plus beta into RB plus RE by RB plus RE plus beta RE. So same thing I will show here. Okay, this one. So 1 plus beta into RE plus RB by RB plus RE into beta RE. Same equation. See, both are same. 1 plus beta into RB plus RE. RB plus RE into plus beta RE. Okay. RB plus RE into beta RE. So from this equation, so 1 plus beta as it is, RE plus RB, same RB. So we have RB, denominator RB is same. Here we common the term RE term. So RE is common means 1 plus beta. So RE is common means 1 plus beta. So RE plus beta RE can be written as RE into 1 plus beta. Okay. So here, this is the equation now. Now we will divide numerator and denominator by RE. Numerator NV and denominator what can we call DM. Numerator and denominator. So this is NM and DM. Numerator and denominator dividing by RE. So what happened? So this is the numerator. So RE by RE. So here 1. So RB by RE. So this one. So numerator and denominator dividing by RE. So this is RE by RE is equal to 1. So RB by RE. So it is same RB by RE. Then here RB by RE. So we are dividing with RE. So RB by RE 1 plus beta into RB by RE. Okay. 1 plus beta into RB by RE. Next, what happened when the ratio, now RB by RE, when the ratio controls the value of stability factor. Yes, correct. If the ratio is very less, like less than 1, that means we are adding 1 plus RB by RE. If this ratio is less than 1 means whatever we add, it is 1 only numerator. Okay, that means here also RB by RE is less than 1 means it is unconsidered. So finally we will get 1 plus beta by, it is negligible means 1 plus beta by 1 plus beta. So this 1 plus beta and 1 plus beta cancel, we will get 1. So stability factor, we will get 1, value is 1, stability factor. But in practically, this base resistance and emitter resistance is not possible to put it as 0. So it is practically, it is having some value. So in ideal case, it is not possible. So always we have to give some RB and RE value. So we have to minimize this RB and RE value so that we will get the S is equal to 1. Stability factor is equal to 1. Okay. So stability factor for voltage divider bias or self bias is less than as compared to other biasing circuits. So that circuit is most commonly used. Okay. So stability factor, yes, for a voltage divider bias, we also called as collector bias, as compared to other biasing technique like fixed bias and collector to base bias. This circuit is most commonly used. Because why this circuit is most commonly used? It is independent of temperature, it is independent of transistor parameter. So that's why it is more preferable for amplifying the any signal. Okay, so stability factor is 1 means it is good. Okay, if you have any doubt. Okay, like I will summarize what I discussed in this session. So in this session, I discussed this thing, voltage divider method or potential divider method in biasing circuit. So by using potential divider method or voltage divider method, we have to maintain the stability factor or increase the stability factor so that we can get the output as faithful amplification. So in previous cases, fixed bias and collector to base bias, these biases stability is poor, so that we go for other alternative, that is voltage divider bias. Okay. In voltage divider bias, whenever we know that it is the independent of VBE beta. So collector current is independent of VBE and beta. So it is one advantage. If the collector current is increases, voltage drop across emitter terminal is increases. Due to voltage drop across emitter terminal is increases means base current is decreases. Because of base current decreases, collector current is minimizing to its original value. So there is no effect in temperature. If temperature increases, nothing will happen. So circuit works fine. That's why this potential divider method or voltage divider method can be used as a biasing method in many amplifier circuits. So stability is more in this voltage divider circuit. Okay. Okay, thank you.